in the last video, I talked about what capacitance is, and in this video, I'm going to give you a new equation for capacitance. And remember, capacitance is the capacity for a capacitor to store charge. And I'm going to talk about this equation, and I'm going to first hopefully show you why this equation makes sense, and then afterwards, I'm going to kind of prove it to you mathematically, so this equation is kind of dialed in your head and you know exactly why this equation works. So the equation reads as the capacitance for two parallel plates. So I should probably write parallel plates. The capacitance for parallel plates is equal to epsilon naught times the area, the area of each plate over the distance between them. So if I were to draw in my capacitor, right, hooked up to maybe a battery here, the area, right, because if it's like a parallel plate, so it would look like this if I were to draw kind of a 3D view here, and then, right, so they are separated a distance kind of between each other, and they each have a certain area A. So maybe it has an area A, this one also has an area A, and the distance between them is D. So I'll say this is D, and then this is D. So what this equation is suggesting is that if you increase the area of each plate, you're increasing the capacitance. And if you increase the distance between the plates, you're decreasing the capacitance. So let's just remind ourselves, the capacitance is equal to Q over V. It's the ratio of the amount of charge on each plate over the electric potential between them. And if we're dealing with one capacitor, this electric potential difference, the electric potential difference between them. The electric potential difference is going to be equal to the voltage of the battery. So what I want to first look at is, okay, how does increasing the distance how does increasing the distance decrease the capacitance, right? So let's say we have two capacitors. Okay, so I'm going to make two kind of circuits. We have battery. Let's get something like this, and then I'm going to make this bigger actually. So let's say we have something like this. Alright, so let's say these both have the same voltage, I don't know, 36 volts. Alright, and let's say this one has a bigger distance. Alright, now I'm going to make this actually a lot bigger. So I know that the electric potential difference between each capacitor is going to be the same, right? Because each battery is going to be providing the same exact voltage to each capacitor. So in that case, we know that the equation for voltage is going to equal the electric field between the 2 points, right? If you think about point A, point B, point A, point B. So the voltage difference between point A, or the voltage between point A and point B, is equal to the electric field between those 2 points times the distance. And if you think about the integral, right, if the electric field is not constant, we would have to integrate, but for a parallel plate, we know it's constant. So voltage is equal to E times D. If the voltage is the same, so if this is the same, but the distance is bigger, that means the electric field is going to be smaller for this plate, right? So the electric field is going to be smaller, and we're going to also assume they both have the same area, right? And we're going to kind of explain why. The electric field, I'm sorry, I'm going to explain why that's something we got to keep in mind. They have the same area, and then I'll talk about some other things. So let's say they have same area, and this has a smaller electric field. Well, for a parallel plate, we know from Gauss's law that the electric field between two parallel plates is going to equal the surface charge density over over the epsilon naught. right? And that's from Gauss's law, and you can watch videos on why this is the case. But the idea being that, okay, if we have a smaller electric field, we must have a smaller surface charge density. Now, if you have a smaller surface charge density is, and those are my parents, sorry about that. Surface charge density, I don't know why my parents are laughing so much. If we have surface charge density, it's going to be equal to Q over A. It's the total amount of charge per area, so this is the same as Q over A, right? So in that case, if you have the same area and you have less surface charge density, that means you're going to have less charge, right? So if they're the same area, we have a lower surface charge density, then this capacitor is going to have a less charge per what's the word? Less charge per area. So if it has the same area, it's just going to be less charge overall. So that's why a greater distance, right, for the same voltage is going to lead to a smaller amount of charge. Hence, you get less capacitance when distance increases. Okay, so what about if the area increases? Let's say we kept the distance constant, but what if the area increased? Well, if the area increases, what's going on is, well, the same voltage and then the same distance, that means you're going to have the same electric field, right? Because the distance between them is the same, so and the voltage between them both is the same, so you're going to have the same electric field. Well, that means that E is going to equal, surface charge density over epsilon naught. So if you have the same surface charge density, right, that means if you have a bigger area, to get the same surface charge density, you need more charge, right? So if you think about Q over A, if this remains constant for both of these and you have more area, you got to have more charge. So when you increase the area, you're increasing the charge for the same voltage, hence more capacitance. So right there I just showed how increasing A increases the capacitance and how increasing B decreases the capacitance. Now I'm going to very quickly show you where this equation comes from, right? Why is there an epsilon naught there? You might even start imagining why there is an epsilon naught in there, but we're going to very quickly derive this equation. So we know that C is equal to Q over V. So if C is equal to Q over V, V is equal to the electric field between the two parallel plates over the distance between them. Now, what is the electric field equation for parallel plates? It's the surface charge density over epsilon naught. So we're going to get surface charge density times distance over epsilon naught, right? Because I just did that multiplied by distance. And now we have a fraction, and we're dividing by a fraction. So we would multiply the reciprocal, epsilon naught over surface charge density times distance. And now C is going to equal epsilon naught Q over, so surface charge density is equal to Q over area times distance. So this now, so that would mean C is equal to epsilon naught Q over, and I'm writing a little bit slanted here, but if I just kind of bring this over here, that means that C is equal to epsilon naught times Q over Q times D over A. Okay, so now multiply reciprocal again, we get C is equal to epsilon naught Q times A over Q over D, Q times D, right? So all of that in the denominator. Hey, look, Q's will eventually end up canceling out, and you get C is equal to epsilon naught times area over D, which is that equation. So you can see how Q cancel out, and yeah, it uses the Gauss's law reasoning, kind of that we were talking about, how, okay, if I know it's going to have the same voltage, more distance, less electric field, that less electric field means less surface charge density, which would result in less charge. So yeah, that is what the capacitance depends on, or what affects the capacitance of a capacitor.